burnt edges, tear out that ruins a clean cut, a bit that spins for 10 seconds and barely marks the wood. None of that is the router's fault. It never was. A router is just a motor spinning at a fixed set of speeds. Almost every result people blame on the tool actually comes down to the bit, and almost nobody explains why. By the end of this, you'll know exactly which bit to reach for and when, why edges keep burning even when technique feels fine, and the one feed direction mistake that causes more kickback than a dull blade ever will. This isn't a glossary of bit shapes. This is the handful of things that actually change what comes off the router. Start with shanks, because this decision gets made before a single cut. Router bits come in two shank sizes, a 1/4 inch and a 1/2 inch. When a router accepts both, the 1/2 inch shank wins almost every time. More metal in that shank means less flex under load, less vibration at speed, and a cleaner cut, especially in hardwood. A 1/4 inch shank has its place in smaller trim routers and lighter work, but it's also the quiet reason a lot of what gets called router chatter isn't really the router at all. It's an undersized shank trying to control a cut it was never built to handle, flexing just enough under pressure to leave a slightly wavy edge that looks like a technique problem and isn't. Then there's how deep that shank sits in the collet, which almost nobody checks. A bit needs enough shank buried in the collet to be gripped securely along its full contact length, not just pinched at the very tip. Insert it too shallow, and the bit can work loose under vibration during a cut, which is its own kind of dangerous. Insert it too deep on some bit designs, and the collet can end up clamping down on the transition point where the cutting profile begins. Rather than on the plane shank it was designed to grip. The fix is simple and takes 5 seconds. Seat the bit fully, then back it out slightly, generally around a 1/16 of an inch, before tightening. That small gap keeps the clamping force on the shank itself. Now the mistake that shows up more than any other, running every bit at the same speed. Most routers have a dial numbered 1 through 6, and beginners leave it in the middle for everything they own. But bit diameter and safe RPM have an inverse relationship. A small 1/4 inch straight bit can handle a high speed just fine, because the outer edge of that small bit isn't traveling very far per rotation. Put a large panel raising bit, something 3 inches or more across, in that same router at that same middle setting, and the outer edge of that bit is moving through the air and through the wood at a completely different speed than the small bit ever did at that identical dial position. That's not a clean cut anymore. That's friction, heat building at the edge, and a bearing working far harder than it was designed to. So the fix seems obvious: slow the router down for big bits. And that's correct, but it creates a new problem nobody warns beginners about. At a lower RPM, if the feed rate through the wood doesn't slow down to match, the result isn't a clean cut either. It's chatter, a rippled, scalloped edge that looks exactly like the bit was dull, even when it's sharp. Slower spin has to be paired with a slower hand feeding the wood. Get the RPM right, but keep feeding at the old speed, and the router just trades one bad result for a different one. Here's where it actually gets worse, because feed direction isn't fixed. It flips depending on the setup, and almost nobody explains that part clearly. On a router table, with the bit spinning clockwise as viewed from above, the workpiece gets fed left to right, moving against the direction the bit is spinning at the point of contact. Take that exact same bit out of the table and run the router handheld instead, free hand on top of the workpiece, and the reference point flips completely. The router is now above the wood instead of the wood moving past a fixed bit below a table, and feeding it the wrong way at that point means the spinning bit grabs the material and pulls the whole tool along the edge on its own. Fast, with almost no warning beyond a split second. This isn't a sometimes mistake. It happens every single time the direction is wrong, not most of the time, and it's the single biggest cause of router kickback. Ahead of a dull bit, ahead of bad technique, ahead of almost anything else that gets blamed. People get told the rule, feed against the rotation, and that rule is true, but it's close to useless without knowing that the reference point for the rotation changes the moment the setup changes from a table to handheld work. Climb cutting sits right next to this, and it's worth naming because it's the deliberate version of feeding the wrong direction. Feeding with the rotation instead of against it, on purpose in short controlled passes, can produce a cleaner cut with less tear out on certain grain, especially right at the very end of a pass where standard feed direction tends to blow out the last bit of material. But it only belongs in the hands of someone taking a light pass and expecting the pull, ready for it, using both hands firmly on the tool. Done as a beginner's default feed direction instead of an intentional light finishing pass, it's the same grab and pull described above, just chosen instead of accidental. Here's the part that reframes an entire bit collection. Carbide isn't the upgrade option sitting above a normal bit. It's the difference between a bit that holds an edge through a project and one that quietly stops cutting cleanly halfway through it. Standard high-speed steel dulls fast in anything beyond soft, clean, knot-free pine. Once it's dull, the result isn't a rough cut, it's a burnt one, because a dull edge stops slicing the wood fibers and starts rubbing them instead, generating heat at the point of contact. And burn marks get blamed on the router, on technique, on the wood species itself, almost never on the bit that actually caused them. Carbide holds its edge through hardwood, through plywood, and through MDF, which chews through high-speed steel edges fast because of the glue and resin content bonding those sheets together, glue that a steel edge simply isn't built to survive contact with for long. So if burning on oak, on maple, or on MDF has ever gotten blamed on operator error, on hand speed, on the router itself, there's a real chance none of that was the actual cause. It was a low-cost steel bit doing exactly what a steel bit does. The moment it meets a material, it was never suited to cut in the first place. That changes what actually needs to sit in a bit drawer. Not 40 bits bought over years without much thought. 5 in carbide cover the overwhelming majority of real work. A straight bit for dados, grooves, and mortises, a flush trim bit for template and pattern work, a roundover bit for eased and softened edges, a chamfer bit for decorative angled edges or simple edge breaking for safety, and a rabbiting bit for lap joints and case construction. A few more are worth knowing, even if they're used less often. An OG bit produces the S-curved decorative profile common on picture frames and cabinet edges. A cove bit cuts a concave curve, often paired with a straight bit to build a full cabinet cornice profile in 2 passes instead of one complicated one. A dovetail bit, run with a jig, cuts the interlocking joint used in drawer construction, and it's one of the few profiles where the jig matters as much as the bit itself. Bearing-guided bits deserve their own mention because the flush trim, roundover, and chamfer bits already mentioned usually fall into this category. These bits ride a small bearing against either the material's existing edge or a separate template clamped to the workpiece, and that bearing does the steering, which means the accuracy of the final cut depends entirely on the surface that bearing is riding against, not on the sharpness of the cutting edge. A smooth, accurately shaped template produces a smooth, accurate edge. A rough or wavy template or a rough existing edge on non-guided passes gets copied faithfully onto the new cut, no matter how new or sharp the bit is. People sand and fuss over the workpiece and never think to check the template it's riding against. One more habit worth building. Take a moment on bit balance and wear before every session, not just when a cut looks wrong. A bit that's been dropped, or one with a chipped carbide tip, doesn't just cut worse. It can vibrate at speed in a way a sharp, undamaged bit never will. And that vibration is felt through the router body long before it shows up as a visible flaw in the cut. Wipe pitch and resin buildup off the cutting edges between projects too. A gummed-up bit behaves like a dull one, burning and tearing instead of slicing, and it's often mistaken for a bit that needs replacing when it just needs cleaning. There's also a difference between fixed base and plunge routers that changes which bits even make sense to use. A fixed base router sets the cutting depth before the bit ever touches the wood, which works fine for edge profiles, roundovers, and chamfers where the bit only ever contacts the outside edge of the material. A plunge router lowers the spinning bit straight down into the middle of a workpiece, which is the only safe way to start a cut for mortises, stopped grooves, or any dado that doesn't run off the edge of the board. Trying to start an interior cut with a fixed base router means tipping the tool into the wood at an angle and hoping, which is exactly how bits get chipped and edges get gouged. If the cut needs to start away from the edge of the board, that's a plunge router's job, full stop. Straight bits themselves aren't all the same either. A standard straight bit cuts flat across the bottom and clears chips upward and out of the cut as it goes. A spiral upcut bit does the same job but pulls chips up and out even more aggressively, which is useful for deep mortises where chip clearance matters more than surface finish, though it can pull grain up and splinter the top face of the cut. A spiral down-cut bit pushes chips downward instead, which leaves a cleaner top edge with far less tear out, at the cost of chips packing into the bottom of the cut instead of clearing away. Picking between them isn't about which one is better. It's about which surface of that particular cut actually needs to look clean. Curved cuts change the climb cutting conversation too. On an outside curve, standard feed direction works exactly like it does on a straight edge. But on the inside of a curve, the direction the bit needs to travel to stay against the rotation reverses partway through the curve. And that reversal point is exactly where beginners get caught off guard and either climb cut by accident or fight the router through a section where it wants to grab. Slowing down through that transition point and expecting the bit's behavior to change, there's the difference between a controlled cut and a surprised hand. Dust and chip clearance matter more to bit performance than most people account for. A router bit spinning inside a cut that isn't clearing chips is effectively recutting material that's already been cut once, which dulls the edge faster and generates extra heat at the cutting surface. Hooking up a dust extractor or shop vac to whatever port the router or router table has isn't just about a cleaner shop floor. It measurably extends how long a bit stays sharp before it needs sharpening or replacing. Storage plays a bigger role in bit life than it gets credit for too. Carbide tips are hard, but they're also brittle, and tossing bits loose into a drawer where they knock against each other chips those cutting edges in ways that are often too small to see and only show up later as a strange, faint burn line on an otherwise clean cut. A block with individual holes, or even the cases the bits came in, keeps the cutting edges from ever touching metal on metal. It also keeps humidity and shop dust off the exposed steel shank, which is worth doing anywhere near coastal or generally humid conditions, since a shank that's picked up surface rust won't seat as securely in a calle as one that hasn't. None of this was ever really about the router. It's a motor spinning a bit at a chosen speed, nothing more complicated than that underneath it. Everything past that, the burning, the tear out, the sudden grab of a kickback, is the bit, the RPM, and the feed rate doing exactly what they were always going to do under those specific conditions. Get the shank size right, match the RPM to the diameter instead of parking the dial in the middle for everything, get the feed direction correct for whichever setup is running, and reach for carbide the moment the material gets harder than clean pine. Get those right, and the router stops being the unpredictable tool in the shop and starts being the most reliable one in it.